So, Zach, in the last few episodes, we've gone through some thermodynamics, some statistical mechanics, and the concept of keeping time with iPhones. And I think this has been leading up to what I've wanted to cover from the beginning, which is my reading of Sean Carroll's book. Let me get the title right: From Eternity to Here, which is not From Here to Eternity, which is the other old movie. But yeah, so I finally finished it. It was a lot longer than I thought in terms of time and number of words to read, but I loved it. And I haven't really dug into a pop sci book like that in a long time. And so basically this is going to turn into a Sean Carroll Stan podcast probably for a while, because I'm not only reading his book, but I've gone through his whole Mindscape podcast, which is really interesting.
His Mindscape podcast, yeah.
Yeah, super good interviews with scientists and philosophers. So yeah, lots of Sean Carroll consumption recently. But this book is all about the concept of time and the arrow of time. And Sean Carroll has lots and lots of public talks on that topic. And this book really lays out the physics background for the concept of the arrow of time, which has been tackled by philosophers and scientists for a long time. And I think one interesting way to distill the problem down into a simple question is, why do we remember the past, but we don't remember the future? Like, why is there that asymmetry when in physics, I think we've talked about a few times, all the laws of physics are time reversible in some sense. Like you can work out a way to see physics use the same exact equations, just with a reverse of the direction of a parameter in those equations called time. And so if that's true, why don't we see that on the macro scale of the past versus the future? Like, why is there the concept of causality? Why do eggs roll off the counter and break, but we never see them collect themselves and spontaneously reappear on your counter whole? So there's that macroscopic asymmetry, which, as you could probably guess, is going to touch upon entropy, which we've been talking about in the past.
Yeah.
In an earlier episode.
Yeah, maybe to like highlight that example a little bit more.
Yeah.
Like as a egg is falling off of a counter, like if you tell me where it is and like what its momentum was at a certain point in time, like while through that fall, we can tell you where it was at any point up until the time it like left the counter, or where it will be. Like, so if you took a snapshot mid-fall, physics can tell you at what point in time was it in any position before, and what point in time is it any position later until it hits the ground. So like all that is totally time reversible. We know all the information there, but it's the cracking part that's like, we can't, once it's cracked, it's splattered all over your floor. We can't like reverse that. Right.
And Sean Carroll brought up an interesting point about the concept of reversing time in the equations and saying that they work in that if you think about planets orbiting the sun, for example, it's not that the actual physics, if you took a video of the planets orbiting and then played them backwards, yes, that would work. But what's actually happening is that we're technically flipping the direction of the momentum, like the vector of momentum, which it's not exactly playing the physics backwards, because we do have to flip the momentum. But all that to say, we give ourselves these graces of saying, if you can figure out a way to arrange things such that time can be reversed, then we consider it a time symmetric theory of physics. So in particle physics, there's the concepts of CP and T symmetry. We might have touched upon that a long time ago when we got into particle physics, but charge, parity, and time symmetry. And a lot of times, or a long time in the past, people thought that each of those individually was a conserved property of physics. It was required to be conserved, that charge is always conserved, parity is always conserved, and time, it's not so much conserved, but it's a reversible property. And each of them have individually been shown to be broken, that you can have physics that breaks the charge symmetry, and also physics that breaks parity, and also physics that breaks time asymmetry. But you can work out a rule of particle physics that has all three of them conserved, and that's still okay. So that's kind of like the reversing the momentum to get your time symmetric theory. To get it back, you got to flip the momentum around for the planets to orbit in the sun. And in similar ways, you can work out particle physics theories that you have to do some other flippings. You flip charge, parity, and time, you're good. You got a working theory of physics. So I think all that to say, there's just unique, interesting ways that we talk about time as being something fundamental. And what does it mean to be a time symmetric theory of physics? You got to do a little bit deeper dive into the particle physics stuff to really work it out. But it's there. It's always there. But what's not there is entropy. Like, why is entropy the one rule in physics that is not time symmetric? It is forever increasing. Or staying the same at best, but it's always going to increase in general. So why is that one the one that breaks? And so we talked about this with StatMech. We talked about Boltzmann conceptualizing entropy, where he was really the first to think about the counting of states, the microstates that make up a macrostate. So we observe some macroscopic property of something, and underlying that macroscopic value for, say, pressure is a collection of microstates. And so Boltzmann was thinking about states evolving from low entropy macrostates into higher entropy macrostates by naturally just finding themselves in a situation that's more likely to be in existence. So that's, I think, the fundamental nature of the second law is it's just more likely to be in high entropy. So it's just forever going to increase towards that high entropy situation. And then it'll increase until it maximizes the entropy. And that's when things we say are in thermal equilibrium. No more energy is exchanged. Nothing's happening really. It's nice and happy and stable. So at this point, cool. We can talk about eggs. We can talk about macroscopic entropy values for scrambled eggs, cracked eggshells. But what about our whole entire universe? Why is that evolving towards a higher entropy end on the whole? And why aren't we just already in the most likely situation? So that's kind of the philosophical, cosmological question. Like, why are we so special? Like, we look around and we're in a low entropy state for all the possible states that our universe could be in. So why are we special? And we can talk about anthropic principles where we talk about like, well, we have to be because that's where we are and that's who we are. Otherwise we couldn't exist. But it's not really satisfying to say that. Those kinds of answers to like, why is physics tuned to this particular way? The answer is, well, if it wasn't, we wouldn't be here to be able to ask the question. So by asking the question, they must be in that way because otherwise we couldn't ask it.
Yeah. I mean, it does make some sense to me, right? Like if you looked at like, if you just imagine that there's all possible states of parameters to make up the universe, that it's not likely that all of them produce life or are able to have, like a stable universe with life and stuff. So like if there is one and they're like if it can eventually like just cycle through all of them until there is one with life, then that's where we're going to find ourselves because we can't find ourselves in any of the other ones. So yeah, kind of like I follow it, but it almost feels tautological. Yeah.
I like what happens when you enforce the anthropic principle is you work out, well, if that's true, if the rules of physics and the state of the universe has to be one in which we exist to be able to ask the question, why do we exist here? Then you end up with what are called Boltzmann brains as being the actual most likely situation, which we'll talk about this later, but there is a known state of the universe that is the most likely highest entropy state, and it's just called de Sitter space. Have you heard of that term?
I have. I don't know what it means, but I have heard it.
It's basically flat, empty space with a small positive cosmological constant. So we, in theory, will eventually lead to a de Sitter space universe, just complete emptiness, maybe some quantum fluctuations in that space. And it's a small positive energy everywhere. But we would expect the universe to evolve to that most likely situation. Basically, let's run entropy as high as we can. That's the entropy of de Sitter space in a universe size amount of space. And what the Boltzmann brains say is that if you think about, well, the physics and the state of the universe has to be in such a state that we could ask the question, why are we in this state? what is most likely to be the situation is we're not actually humans. We're just these brains that fluctuated out of de Sitter space, and we should be surrounded by complete emptiness and have a brain that can ask the question just by random chance of fluctuations. If we let the universe run for eternity, that's the most likely way that we would have a universe with observers like us who could ask that question.
So yeah, that's like one of these arguments where like if you let infinity happen, every option is available to you.
Right.
So then it's like, what is the highest entropy of those options? Is that kind of it? And it's
exactly. It's like get the most likely space around us, and then let us exist in the fluctuation within that space. And we don't see that. Like, we're not in empty space. We don't see de Sitter space all around us. When we look out into the universe, there's a whole bunch of other stuff. So because of that other stuff, we say, okay, well, it's not just anthropic principle. So I'm going to share a little analogy that I think solidified the concept for me. And the way to fix this, we look around at our universe, which is in relatively low entropy compared to what it should be. What's the most likely situation of our universe? And it's, by definition, astronomical disparity between what we currently observe entropy-wise and what the maximum entropy is. Like, the number of zeros at the end of that ratio of those two things, those two entropies, is enormous. So let's work with not the universe, but a little bit smaller system. And I wrote this up in a Reddit answer to somebody asking about time, but I think it kind of makes sense here as well. If we had a tray, I imagine like a baking sheet of like 100 pennies, and we just threw them on the tray and shook them around, we would expect to see some heads and some tails. And we kept shaking. We would probably expect, whenever we look and count up how many heads and tails, we would expect to see 50-50. On average, that's the most likely situation. So we would see 50 heads and 50 tails usually. Now, what we currently see is not anywhere near the 50 heads and 50 tails, and I can't even do it with 100 pennies. But let's think about what would happen if we just sat there and we thought the tray had been shaken a few times. When we look and we see 3 heads and 97 tails. Clearly something happened. Like, what led to that such low entropy situation, low configuration, low likelihood state? We would think either somebody went in and manually flipped them all over from something, like somebody had control over it, or somehow we started with all tails and we've only shaken a couple times and we just now have 3 heads. But we're working up to 50 eventually.
This is kind of like sounds like a God versus maybe evolution sort of argument.
Yeah. I mean, yeah, you could say, well, God was there and flipping the pennies so that they always were less likely to be heads than tails. Tails is more likely for some reason. God likes tails. So you could say that. But what people really point to and say is, well, we have to have a hypothesis of the past. And this is literally called the past hypothesis of the universe, where in the early universe, we were very low entropy. And we are currently in the middle of the shaking of the tray of pennies, increasing towards the 50-50 maximum entropy state. We just happen to be in like the 3 tails state, where we're not at the lowest entropy. We had a lower entropy past, but we're on our way to the higher entropy future. So that's generally the way we understand what we observe in the universe, entropy-wise. We're in some very low entropy state, but that's because we were in an even lower entropy state earlier, which is what the past hypothesis says.
I'm going to ask the stupid question, I think. I got to imagine, when we talk about the Big Bang, if we just, let's posit that as the start of the universe, that has to be like the lowest entropy state, I would imagine, right? Because it's just a single point. That's it. It's there's one configuration and it's in it, I would think. Well, I don't know for sure.
Yeah, we'll get there. And it's not a single point, but yeah, we don't really know. But we'll talk about what that early low entropy configuration was. But yes, it connects to something that we could consider a Big Bang. And there's ideas about how that came about. But yeah, the past hypothesis is the answer. I mean, it doesn't really answer it because you're just like, well, why were we in low entropy? We just keep asking why. We don't have great answers for why, but I'll talk about a few of them. But the fundamental question of why do we remember the past but not the future is because we're constantly increasing entropy towards the higher entropy state because we had a low entropy past. So that's how our brain perceives the passage of time, is the shaking of pennies where the number of tails and heads approaches 50-50. And we're not even close to that yet. So we're still evolving. So we notice as the pennies flip and we approach 50-50 that the time is moving forward. And that's the direction that we consider the future.
And just to be a little clear on things, I think, is this doesn't necessarily mean that like my personal entropy is like necessarily increasing every minute all the time, right? Because
No.
it's the whole system. You have to take me
Right.
plus the rest of the world,
Yes.
or the universe even, as the increase in entropy. So like it's not like you are the listener increasing in entropy all the time, and that's why you remember things necessarily.
Right.
Okay.
Yeah. It's Sean Carroll used the analogy of physics doesn't care about directions, like out in the middle of space, up, down, left, right, forward, back. Those are all equivalently likely. Physics works the same in all those directions, except when you bring the system close to a large massive object, like on Earth. We're close to a huge source of gravity, which flips it adjusts the symmetry of the physics in such a way that down is very different than up. Things behave differently when they're moving downward than when they're moving upward, because we're near this huge source of this affecting space-time thing, which we call Earth, right?
Yeah.
So we're nearby, quote unquote, a low entropy situation, similar to how we're nearby a large massive situation in Earth. But the low entropy past makes the laws appear like there's a difference between the past and the future, when really the laws of physics themselves don't care about that. We just need to work in this source of a weird situation that's not typical. It's not empty space. There is a entropy of the past that's lower than the entropy now, and it's lower than the entropy of the future.
Yeah, I like that. So there's just it's a symmetry breaking system right now. Basically
the Big Bang basically broke the time symmetry of what we perceive as time. Eventually, before we go into the past, because there's a lot of details to talk about there, but we can cover the future. There's a Katie Mack book. Do you know who Katie Mack is?
No, I've not heard of Katie Mack.
She's a physicist, a physics professor, I think at North Carolina. And she wrote a book recently called The End of Everything, astronomically or astrophysically speaking. So it talks about different ways that the universe ends. And Sean Carroll touches on this a little bit. And one idea is that we reach the max entropy state, which you probably heard of as the heat death of the universe.
Yeah.
Which is, just empty space. That's that de Sitter space stuff where everything is just in thermal equilibrium. There's no more entropy increasing. And at that, if we were to live there, which we can't, but if we could, we wouldn't perceive time passing. There would be like the eternal shaking of the pennies flipping, but it would always be 50-50 and we wouldn't notice anything happening because there is nothing to happen. No physics, no thermodynamic engines could exist because everything's in thermal equilibrium. We're just in a steady state.
There's, just like you were saying with the Earth mass, there's no way to define a direction anymore. Basically,
Mm-hmm.
There's nothing to break the symmetry. It's all
right.
All the same.
Yeah, the physics keeps happening. Well, there's nothing there to cause physics to happen. It's just empty space. But what's interesting, so maybe I'll bring up an early universe idea, is that we came from a de Sitter space of huge emptiness that was at its max entropy that has existed who knows how long, of just max entropy, de Sitter nothingness. But in that, because of quantum fluctuations, there may have been a space where a little patch was smooth enough and it could branch off and pop out a low entropy version of de Sitter space. And I might not be describing that perfectly, but the idea is it's called a baby universe. The de Sitter space gives birth, I guess, to baby universes.
Okay.
So it's a little bubble that just pops into existence that all of a sudden separates off from the universe it came from. No way to connect to it. There's actually, I think there's a wormhole that temporarily connects them. It's like the picture of when you drop water drops into a plate of water and the little the little splash up, that's like the water's surface is de Sitter space, and the little droplet pulling up out of that with the little tiny connection, that's the baby universe. And then it disconnects and it goes off and it's its own universe. And so the idea is that we came from one of those baby universes that popped out of a de Sitter space. And that baby universe just started, it could start only because it was at such a low entropy beginning. And we just came from there. That's the Big Bang, is our little baby universe pop, which I think is weird and interesting.
Yeah, I kind of love when you get to this level of physics where you're not entirely making things up. Like you definitely hold yourself to some, physical laws that we try and obey or think maybe are slightly different now versus then type of thing. But at some point too, it also just seems like what is the theory to test this? Like,
yeah, apparently they've worked out. It's more than just like a cute description, but like it's been hypothesized that is what's happening. And it's basically a multiverse theory, because in theory, the de Sitter space could just give birth to a bunch of baby universes that all have their own, maybe slightly different beginnings, and they evolve differently from different places. And we just happen to be one. I mean, it kind of does bring back the anthropic principle, and that we're in a baby universe that had a low entropy beginning and evolved to us being here, asking the question, where do we come from?
Yeah, I've heard about this before, and I guess I'm wondering, one thing is maybe I'm conflating two ideas, but is this also related to like our universe, our baby universe that is now, maybe it's a toddler universe, is that able to interact with other universes in any way by like them expanding, or is it just they're always separate?
They're always separate, isolated, no way to pass information. I think Katie Mack's book talks about this a little bit. It's funny because it's simultaneously an explanation of what happens at the end of our universe, but also maybe the beginning of our universe. Like, where do we come from? And we keep branching these new universes from these high entropy eventualities of universes.
Yeah, you always end up in a de Sitter space, which is maybe an adult universe that can then have a baby universe and you start all over again.
Exactly. And so what's interesting is, as we talked about the pennies shaking up and down, like that it does have a time component to it. Like, I'm shaking pennies and I shake them again and again and again. So there's like some evolution of steps that are happening there, but no thermodynamic processes could come of that stuff, except when there's a fluctuation of a baby universe. One of them could be starting from a situation and evolve forward in time of de Sitter space time. If there's it's kind of weird. You have to come up with a master direction of time, but the universes can pop in and out of existence flowing in either direction of that master universe. So what we might think of as forward time progression might be the opposite of this super master time that's outside of our universe. But we wouldn't know. All we know is just the entropy is increasing in that direction. So we're evolving towards that and think of that as the future.
Yeah, I'm trying to wrap my head around all that. I think maybe I'm wrong here, but I'm thinking is it kind of like, okay, if there is de Sitter space, that's the highest entropy there is, let's say, but then you pop off a baby universe, you kind of measure maybe the baby universe is popping off as a way of like seeing something happen in de Sitter space.
Right.
Okay. And then, but then I'm almost wondering that wouldn't, if you include the parent de Sitter space and then all the baby universes as one massive universe, wouldn't entropy is still increasing now entirely throughout the entire universe? Exactly.
So that's kind of the solution to the second law keeps going, because you can always increase entropy by these baby universes. Like, there's a maximum entropy of the bigger universe that maybe we popped out of, and we're adding to it continually by our baby universe increasing in entropy. And who knows, maybe that one was originally a different baby universe from another, I don't know, I'm calling them master universes, whatever they are, old universes. So yeah, the entropy continues to increase no matter what, in any direction of time.
Yeah, like that's the the only way forward.
Yeah, exactly. Because it gives birth to these low entropy little configurations. And I think so I'm going to slightly diverge into a different topic, but it's somewhat related in that the baby universe pops into existence in a random fluctuation state where, this little bubble of de Sitter space just has stuff happening in it. Black holes pop in and out of existence, quantum fields. One of those fields is hypothesized to be what's called an inflaton field. Have you heard of that?
Inflaton? No, that's entirely new to me. Inflaton.
So let me back up and just say a kind of passing remark about fields. What we see as particles and fields in quantum objects that we know of, there very well could have been other fields at very early universe that we have no idea what they were. And there could be just totally different physics in particles that have fields back then. One of the ideas is that there's a particle that in quantum mechanics we would call the inflaton field, which another name for it, Sean Carroll uses this. I don't know if he came up with it and anyone else uses it. It's kind of a dumb word, but dark super energy.
Super energy.
Yeah, not just dark energy, but I think it's dark super energy or super dark energy. But that's the relativistic version. And then the quantum field version is the inflaton. And all this is leading to the concept of inflation, which Sean Carroll gave a 50-50 chance because we just don't know, but it does answer some really nice questions for us that we have about the early universe. And I'll get to what those are in a second. But the concept is the baby universe is just this quantum fluctuation of randomness, black holes popping in and out of existence, whatever. And then this inflaton field takes the baby universe and inflates it massively. And Sean Carroll gave the number in the book. And in my head, I was trying to think of it like, if I have a circle on a piece of paper that's the size of a penny, it would inflate to like Jupiter or something like that far, that big. And it all happens in like 10 to the minus 30th of a second or something ridiculously slow, fast, opposite of slow.
Yeah.
But yeah, to go from a penny to Jupiter size. And then I did the math with the number that he gave. And it's take a circle the size of a penny and inflate it to the size of the distance to the next galactic supercluster.
Jeez.
That's how big that inflation is in that small a time. So, so superclusters, if you don't know, we have us in our solar system, in our galaxy, the Milky Way. There's other galaxies around us that form clusters of galaxies. And then there are clusters of galaxies. Those are superclusters. And they're little clumps of clusters of galaxies of stars that are separated by, I had to look up what the prefix is. It's Yato, I think, the capital Y. 10 to the 24 meters. Yeah. So 10 to the 24 meters is the distance to different superclusters. So we're in something called the Lanika supercluster. And there's the nearest supercluster to us is the Centaurus supercluster. So they've given names to these clusters and the distance between them. That's how much a penny-sized circle would inflate in 10 to the minus 30 seconds from the inflaton field. So all that to say, it expands so much and just basically stretches out space and everything in it to a point where all those fluctuations just vanish because they're not important anymore. And the guy that came up with this, Alan Guth, I think that's how you say his name, Guth, Guth, he came up with this idea and he figured out that it explained a lot of unanswered questions. So Alan Guth was trying to explain why we don't have magnetic monopoles. And so his answer was, or with inflation, is that imagine that penny-sized circle and sprinkle some pepper in it, something like that. Those are the monopoles. And right. in physics theories, grand unified theories, back when this guy was working on stuff, it was predicting monopoles had to exist. So he was trying to answer, why don't we have them anymore? And inflation solves it by saying, okay, imagine the universe was peppered with these monopoles, magnetic monopoles, and it was all in the size of a penny, and then stretch that out to the distance between superclusters of galaxies, and the same amount of peppers in all of that space, you're just not going to find them anymore. And so that was his answer to the monopole problem. It doesn't stop there. It explains a lot of other questions. But what the theory also says is that the inflaton field decays into the matter and radiation that we see today. All of our particles came from that inflaton field decaying. After it had stretched to what it is, we're left with normal dark energy and the matter and radiation that we have.
Well, so, okay, I kind of want to wrap back to the monopole slightly question
Sure.
really quick, if that's okay. I'm wondering if this also is a reason why, but I still have a follow-up question. If it is supposed to be, we have the antimatter matter like discrepancy in the universe. Because I would imagine you can maybe make the same argument, like pepper in some antimatter into that small space and then now spread it out to giant. And then there's just a small amount of antimatter floating around now, or at least the density of antimatter is decreased greatly.
I'm not sure. Yeah, I don't know if that's part of the same solution. Sean Carroll definitely didn't say that in the book, but it could be.
Well, my follow-up question to both of those, though, is so. But let's just say the monopole, since that one was made, would be why would there be less monopoles to begin with? We wouldn't have an answer to that, but that's kind of right. I think the follow-up question.
Well, I think the fix is that the inflaton field does not decay into magnetic monopoles for some reason. I don't know why, but it only makes dipoles and other particles that we see. But yeah, I don't know enough about it to answer that, but I know that he was trying to answer the monopole problem specifically, stumbled on the concept of inflation and the inflaton field in the early universe, and he said, okay, that solves it. By the way, the penny to the galactic supercluster distance, that was me starting from the penny. I think the actual size is squeeze the universe that we know of into the size of the proton, and then it inflates to the size of a grapefruit in 10 to the minus 30 seconds. Which is the same ratio as a penny to the supercluster distance, which is surprising.
Yeah, I think just the penny though is a little more. It's hard because both of those bounds, like the supercluster distance, kind of it's far, but it's hard to grasp. But then on the other example, the proton, it's like, can you actually really imagine how small a proton is? That's hard.
Right. Okay, so inflation solved or answered or gave a possible answer to the monopole problem. What it also did was give an answer to what we observe in the universe, which is, I don't know if you've heard this, but the universe is flat. And it's kind of an unanswered question of how flat, but as far as we can tell, it's extremely flat, meaning there's a potential for the curvature of the universe to not be flat, but to have a positive or negative curvature. Like it could wrap around on itself like a beach ball, or it could be a negative curvature, which is like a potato chip, like a Pringles chip. Those are different possible curvature shapes that the universe could have. And the idea was if it's not zero curvature, which is flat in the early universe, then it would eventually decay, like it would ball up on itself or it would Pringle out on itself, whatever that is. But it's a teetering balancing problem of you have to be exactly zero to be so flat as we see it now. So the analogy is like, imagine balancing a pencil on its point. In theory, you could do it, but wait long enough and it's eventually going to tip over. And so that's kind of what we're seeing in the universe is that we're balanced on the tip of a pencil with our curvature problem, and it's not changing, which means we are the exact flatness required to be flat forever, which is bizarre, unexpected.
Well, yeah, I think, but if you go back to like the anthropic idea, you know, and let infinity solve everything for you, then it's just another, okay, we're in the bubble, the baby universe where that was the outcome of the inflaton field decaying and everything. Like,
right. Like we have to.
Yeah. You know, we're only focusing on this one universe that we're in because we care about it. But there were, a trillion, zillion other universes where this happened and didn't have this same result that we're experiencing now. We kind of, I wonder, I guess that'd probably be the way to think about it.
Right. Yeah. And the reason it solves this problem, the reason inflation solves the flatness problem is, well, you can probably imagine just by inflating that much that quickly, you take a small patch of space and just stretch it out to that size. It just stretches it like a bed sheet, like a fitted sheet over the mattress. It's just going to be flat because it's stretched so far, so fast. Started from something that might not have been flat, like a little curved patch, but by stretching it out that much, it's flattened. And that's why we have a flat universe, is because we live after an inflation.
Gotcha. So physicists didn't like my anthropic argument either. Yeah. Right. So they solved it with another method, which I like more. I like that better.
Yeah. So inflation solves monopoles and solves flatness. Two problems with our understanding of a universe. And then there's a third problem that we recently learned more about, maybe the last few years ago, which is the cosmic microwave background, which is basically light from the early universe. I think it's like 400,000 years after the Big Bang. We all of a sudden had a way to see through the universe. And before that, it was just pure radiation and light. We couldn't see through it. It was all opaque. So that leftover from that moment of transparency, essentially, we still have light shining on us from that time. And it's called the background because it's literally just behind everything we see. If we look at a telescope, it's the farthest thing that we could see, and it's hitting our telescopes from that age of the universe. And it's a microwave radiation because it's stretched out so much in space-time. The wavelength has gone into microwaves, but we detect it everywhere. And the problem, that's not a problem. That we got it. That's cool. The problem is that it's exactly the same number. If you point a telescope, I don't know, left and look at what the microwave background value is, and then point it completely 180 to the right, another part of the sky, it's the exact same number. And that's a problem because in theory, if we run our clock backwards, there's no way for a point on the left side of the visible universe to be the same exact temperature as the right side. Like they must have collaborated at some point, like for them to be as exact as they are. Sean Carroll has a good numerical analogy of saying, ask 1,000 people to pick a number between 1 and 1,000,000. And what we see in the microwave background is it's as though every single one of those 1,000 people picked a number between 836,820 and 836,830. 1,000 people asked to pick between 1,000,000 numbers, and they come up with that tight of a range. That's how close the values are on any point in the observable universe's cosmic microwave background.
Yeah, so, I just kind of slightly emphasize maybe, or I don't know, talk about it a different way, is if you look up the cosmic microwave background and you see this picture, there's a lot of reds and blues all over the place, which is very deceiving. Because that seems to indicate that there's a lot of fluctuation and stuff going on. But you have to keep in mind the balance of those reds and blues are what Derek just said. It's a very small window. And really, if you kind of colored it more appropriately, it would all just be one color.
Right. Yeah, exactly. And that's why it's amazing that they even got the picture to have any sort of contrast, that our devices were sensitive enough to pick up those discrepancies. But they are very, very small. Like I said, the 800 and something thousands, you have a range of 10 different numbers in there. So the problem is there's a concept in relativity called light cones, where you can only interact with things that move at the speed of light or slower, and that limits the distance away in the past and physically distance, like the distance in space-time that something could affect you. So if we run our clocks back without inflation, the moment when those left and right sides of the visible universe existed, they're way too far apart to ever have interacted with each other. And so they should be very different. So why is it all the same? Inflation solves it because it says, okay, at some point it came from something the size of the proton, those distances in space, and then inflated away from each other to what we see and thought that they wouldn't be able to interact. But if you have that super inflation that happens 10 to the minus 30 seconds in that little split second time, they could interact. And so they did come from the same patch of space, and they were stretched away from themselves to the point that we see them now. And so the inflation gives the answer to why the cosmic microwave background is so smooth. It's because it came from the same small patch that was the size of a proton. And there's not a lot of variation in that small size of space.
So to kind of reiterate, me making fun of theorists a little bit and their crazy ideas. There's some good evidence out there to support their hypothesis, making it maybe a little bit stronger than just a hypothesis.
Right. Yeah. Let's put some numbers on this. We've been talking about entropy's maximum value and lower entropy past. Where are we? Like, are we 3 pennies in? I said the number of zeros and the ratios of the entropies are just hard to conceptualize. But we have some interesting ways of measuring what the entropies were in the past and the future and where we are now. So in the past, let's talk about non-inflation, just early universe. As far as we can tell, right after the Big Bang, we have some particles that exist. And we know how many particles there are. We know how many particles there are because we know how much stuff there is in the universe. Like, it's just like looking at numbers of stars in our galaxy, how many galaxies we can see, how many are in this space. And we know generally how large the observable universe is. So we know that there are 10 to the 88 particles, which is a huge number. So 100 is 10 to the 2, 1,000 is 10 to the 3, go up from there. We're at 10 to the 88 just counting particles, like literally just protons, neutrons, photons, all that stuff that makes up our universe.
Yeah.
10 to the 88. So what we're saying is squeeze the universe back down to just after the Big Bang when those particles were first in existence. And we get a relativistic gas, essentially. And what's really nice about a relativistic gas is that the entropy is just proportional to the number of particles. So the entropy is some number times 10 to the 88. And the number is like 3. It's not going to affect the power of 10 very much. So 10 to the 88 is the entropy of the early universe, as best we could tell, assuming it's just a relativistic gas. Again, this is not including inflation, which we'll talk about later. So 10 to the 88, that's the low entropy past the past hypothesis. Where we are today. So we can do something kind of tricky to count how much entropy there is in the current universe, which is a lot of work from Stephen Hawking and somebody else named Bekenstein, who worked out the entropy of a black hole is proportional to its surface area. And we can measure that, basically the surface area being the event horizon size, like the shell around the black hole. We can work out the area of that sphere and say, okay, the black holes are this big and they have this much area. And then they work out what the entropy is based on that area. So it's really nice that we can look at the mass of a black hole, figure out the surface area, and then figure out the entropy. We can look at black holes like small stellar mass black holes. They don't carry that much entropy. But what carries most of the entropy in our universe, by the way, if you work out the quantum entropy of just space-time as best we know, the maximum entropy you can have is in the configuration of a black hole. So black holes maximize entropy, which is a key point. Like the stars and the planets and the stuff that makes up galaxies, not as important to the entropy as the actual black hole. And we can actually just assume almost all the entropy of a galaxy is in the black hole at the center of the galaxy. So we know one black hole in the center of a typical galaxy like ours has 10 to the 90th. So that's just one black hole is already bigger than the entire universe had at the Big Bang, or early universe at least. So we know one black hole is 10 to the 90. That's in one galaxy. We also know how many galaxies there are. There's 10 to the 11 galaxies in our visible universe. So it's a really nice simple multiplication. How many black holes? We have one black hole per galaxy that we're considering. So 10 to the 90 times 10 to the 11 is 10 to the 101. That's our entropy. Whatever units. Let's do, joules per Kelvin. But we evolved from early universe 10 to the 88 to current universe 10 to the 101. So right there, we've gone up. The number of zeros in our entropy number has gone up from 88 to 101. What is that? 13? So 10 trillion? Is trillion 10 to the 12?
I think so, yeah.
Yeah, so we've gone up 10 trillion times in entropy from the early universe to what we have now. So the first entropy calculation was from a relativistic gas, which is proportional to the number of particles. Today's calculation is using supermassive black holes in the center of galaxies and figuring out how big those are and how many there are. And then that's most of the entropy is eaten up in those supermassive black holes. Yeah, there's some other entropy like the eggs, but that's so small compared to 10 to the 101 that we just don't worry about it. Okay, that's all good. We've gone up 10 trillion times in entropy. What's the maximum? What's the end result de Sitter space? Well, we know if the entire universe was to become a black hole, and we know that back to Hawking and black holes, eventually those black holes will just evaporate away through Hawking radiation, adding in another technical term. But those black holes started with an entropy before they decayed away. And we can assume the maximum entropy is going to be as though the entire universe was a black hole. So we could work out, take all the mass, everything in the universe, and put it in a black hole. That's the maximum entropy it could have. And we know that that mass turned into a black hole would have a certain area, which we could calculate the entropy from, which would be 10 to the 120, whatever units, joules per Kelvin. That's the max. Yeah, it would even probably go up a little bit from there because of Hawking radiation would dissipate it away to just empty de Sitter space. But we're evolving towards a number like 10 to the 120 from where we are now.
So that would, okay, so just going from 88 to 120 is, 32 powers of 10. Mm-hmm. And we are 13 in there. So we're like maybe a third. We're just slightly under halfway or kind of.
Yeah, it's tricky. It seems like that. But again, if I had one penny that was heads and 100 other pennies, or of a total of 100 pennies, that's a difference of 10 to the 2. Right?
Yeah.
So let's take one penny, and then of 1,000 pennies, that's a difference of 10 to the 3. So just think about the number of pennies you need to go from 1 penny to, what was the difference? 10 to the 32?
Yeah.
So yeah, 1 penny in 10 to the 32 pennies. 10 to the 32 pennies is a ridiculous amount of pennies. Like, I can't even conceptualize how many pennies that is, right? So that's essentially what the early universe was. It was so low entropy. It's the 1 in 10 to the 32 of what it could be. And it's like, why was that the case? That's what the past hypothesis says. And the multiverse ideas and inflation say came from this low entropy state. And we're just evolving towards the maximum entropy. And we just find ourselves, like you said, it kind of feels like a third of the way, but it's not quite, because it's like we've changed from 1 in 10 to the 32 pennies to 1 in 10 to the 19 pennies. So, yeah. And so that's fine. You could probably figure out that that's a ridiculous number. But don't forget, we talked about this before. Entropy is the log of the number of ways you can exist in a certain configuration. So these massive numbers are already after taking the log of something. So in a sense, it's like the real counting of pennies is 10 to the 10 to the 88 and 10 to the 10 to the 101 and 10 to the 10 to the 120. It's ridiculous.
Now you're really unfathomable.
Yeah. How many pennies do you need? I mean, not enough copper in the galaxy to build enough pennies for that. So yes, we experience a middle entropy situation right now that is still extremely unlikely if it was just a random fluctuation. And we have a past hypothesis that says the past was even earlier. It gets even worse with inflation, with the little tiny proton-sized patch that expanded to fill up a grapefruit. That we could work out. And Sean, it's probably like all of those were very hand wavy, but they were like somewhat grounded in some actual numbers that we can measure. This is the most hand wavy of the entropies. It's assuming gets into the space-time configuration of wavelengths of quantum fields inside the little proton-sized space. and counting up how many different wavelengths could you have, starting from just over the Planck length. That's the lower bound of the wavelength. And then you get up to the size of the proton in that space. That's the upper bound, because a wavelength bigger than that wouldn't exist in that space. It's essentially a constant, non-fluctuating anything.
I would think it'd be 2 times, but
I don't know. Yeah, maybe 2, but on the order of, right?
Yeah,
like that size.
Yeah.
So break up the universe in that size into Planck length-sized possible wavelengths up until the size itself. And then that you could figure out to be, and I think he didn't even go to the lowest. He's like, we're not going to consider the actual lowest. We'll take just 1% of that to give ourselves a little bit of grace counting, like not so ridiculous of a number. And it's 10 to the 12 is the entropy of the pre-inflation universe. So that goes way, way lower. And he kind of fudges it, or not fudges it, but brings up the important point that our problem with these answers is that it just kind of assumes a early low entropy situation, but there still remains the question of, well, why was it that low entropy situation? And then he's like, well, inflation. And then he's like, well, that just kind of kicks the can down the road to an even lower entropy situation. Why was that so low? And that's when he brings in the baby universes and little quantum fluctuations out of de Sitter space, which doesn't totally answer the question, but it's an idea.
Yeah. I mean, I think for me, it sounds like prior to this conversation, I feel like we had a pretty good, I was pretty good with how physics is explained from like the post-inflation to now sort of thing. So I feel like I'm a little more confident in the pre-inflation to inflation, like the inflation time. And then, but now I'm still like pre the proton size thing. I'm still like, I feel like that's just whatever you want it to be still.
Yeah, still. I mean, that's the problem, is like we just don't have a good grasp of the physics at that scale, at that time and that space. But yeah, our universe came from something the size of a proton, inflated to a grapefruit, 10 to the minus 30 seconds, and then kept inflating to what we see now.
That's wild. There's a massive amount of energy there too.
Well, that's the crazy thing of the dark energy. Well, I guess super dark energy is like that energy, like literal energy, created everything we see, decayed into stuff that became planets and whatnot, us.
Yeah, and the other wild thing about it too, to me, is just that there's other, in this idea that there's other universes where this happened, and like. I don't know if there's a reason to say that, in some other universe, it decayed to protons and, neutrons and electrons and photons and stuff. It, could have decayed into some other different set of particles with different physics and different cosmological constants and stuff. And
yeah, I feel like there are physicists and philosophers more likely thinking about those kinds of questions of like, they typically talk about a typical observer. And it's like, are we a typical observer? How typical are we? Are there other types of observers that are doing things like asking these questions? How likely are they to exist? I think I said in a really early episode of ours that I read Max Tegmark's book, Our Mathematical Universe, or something like that. I need to reread it because I don't think I got much out of it. But yeah, Max goes through what possible other universes are there. And like, he talks about differences in the ways we think about universes. And I don't totally get it, but yeah, he's a smart guy. I trust that he's at least thinking things through.
Yeah. I mean, there's a fun game you can play, like with physics, and I'm sure they're going beyond this, but just like, even if you're an undergrad, you can kind of do these sorts of things. Like you probably, if you took E&M with Griffiths as your textbook, I think one of the questions, if you got assigned it, is like, what is it? It's like, if there is, I forget what's the symmetry that's broken in Maxwell's equations between like magnetic field and the electric field. It's like, okay, what if you put that symmetry back in?
I mean, yeah, it's the monopoles. You work out physics as though the monopoles did exist. your divergence of B wouldn't be zero. The second equation.
Yeah.
Because you could have essentially magnetic charges, which would look identical to electric charges.
Yeah. And then you can kind of see like, okay, what would that universe be like? How would the physics play out in that universe? And, then you take that further once you know more. People are doing this with like, oh, what if, any of our constants in the universe were different? How would that affect our universe?
Exactly. Yeah. Well, cool. That was my Arrow of Time summary from Sean Carroll's book, From Eternity to Here. I recommend reading it. It was an interesting read, start to finish. He's a good writer, and I hadn't dug into a book like that in a while. I know those pop science books, they always gloss over things, but I think he does a pretty good job of explaining. I would say one thing I wish maybe he did a little more was explain his, like, what he thinks the likelihood of what he's saying is true, because I didn't get that 50-50 number on inflation. It kind of is presented as though that is what happened. But then I heard him in one of his episodes talk about saying he had a 50-50 chance that inflation actually is the explanation that works. So, but it does answer questions and it's pretty cool. It also got me, so looking ahead to future episodes, I've been wanting to talk about black holes for a while. And there's a significant amount of this book talking about black holes and some interesting things that I wasn't aware of. So a topic for a future episode, maybe next one, maybe a few more from now. But yeah, get into some black hole physics that are fun and interesting.
Yeah, I remember doing Schwarzschild radiuses in my GR class.
Yeah, we talked about this. I never had a GR class, so I don't even know. But yeah, awesome. Well, cool. Hope everyone enjoyed this. Follow us on all your podcast apps. I think Apple's changing from the word follow changing from the word subscribe to follow. So I said it right. Good. They're getting rid of the word subscribe for podcast, which is interesting.
And then subscribe on all the other platforms, I guess, until they all switch to follow Max Lead.
Yeah. Well, I think Apple is finally coming into alignment with like Spotify, which has always said follow, not subscribe. And the idea is that Apple's going to release a subscription podcast for payments that you could actually pay people directly. And that's going to be the subscribe, but the free version is going to be the follow.
So they're taking on Patreon.
Exactly. Anyway, all that to say, you can check us out on most podcast apps, tell your friends, and also connect with us on Reddit. It's r/thehyperfine, and on Instagram at thehyperfine.
Yeah, and you can find me on Twitter, I suppose, at Physax, PHYSZAKS.
Yeah, I'm like Tortilla on most social media, and all this information is at thehyperfine.com. And thanks for listening.